at SCL, Mohali, Department of Space. Dr. Rajesh Mehra, Head of Department EC and Coordinator of this program. This program participants at Netter and Network Centers. A very good morning to all of you. The goal of education is not to increase the amount of knowledge, but to create the possibilities for the students to invent and discover, to create the human beings who are capable of doing new things. Well said by Sir Jean Piaget. Now, the destined person to honor us with his presence is Engineer H.S. Jatana. It's my privilege to introduce Engineer H.S. Jatana. He received his engineering education from Beats Pilani and had a brief stint at CMC Delhi as software engineer, wherein he worked on railway computerization projects and later on he joined SCL in the CMOS division. He worked at Rockwell Semiconductor, California, USA, where he was involved in the design of R65 series devices. He has worked in different areas of CMOS and has vast experience on CMOS design, device testing, characterization, test program development on ATE, silicon debugging, process integration, porting of few technology nodes starting from 5 micrometer to sub-micrometer nodes. And he also worked at EMS Austria for 10 months on deputation for porting of SCL schema at the foundries. He has the design of various ASICs and products like energy meter chip, single chip telephone, 12-bit ADC, 14-bit DAC, CMOS imaging sensor, signal processor, SRAM, LDR, LDOs, radiation hardened devices, etc. His areas of interest are low power CMOS design, analog design in DSM, process enhancement, optimization in DSM era. He has initiated many new process development modules like HV, SOI, BiCMOS, CCD process technology with back thinning, materials of group 3 and 4 on silicon for photonics, etc. and APS for camera applications, ultra low power devices, rail to rail OTAs, RHDPs, SRAM, etc. Also interested in spreading VLSI education and has delivered numerous lectures and tutorials on VLSI design and process technology at IITs including Kharagpur, Kanpur, Madras, Bombay, Roorkee, Guwahati, Ropar, Mandi, and various NITs including Hamirpur, Kurukshetra, Manipur, Jalandhar, Nettar Chandigarh, Pune University, Assam State Technical University, Andhra University, PU Chandigarh, etc. He has also conducted a one-day tutorial at 17 VLSI Design and Test Conference and including VDAT 15 and VDAT 16 at Institute of Space Technology at Trivandrum. He, along with Dr. Puri, GD Puri, Head of Anesthesia and Intensive Care, PGI Chandigarh, has 2 patents to his credit for the development of closed-loop anesthesia drug delivery system, which is being used online for critical surgeries like cardiovascular thoracic surgery. Now, the moment has come to add a golden feather in the hat of success. With these words, may I request Engineer H.S. Jatana for his knowledgeable words on the topic of CMOS design.
Thank you, madam. First of all, I would like to express my gratitude to HOD Professor Rajesh Mehra for giving me an opportunity to interact with you. So this particular course is on design of an integrated circuit. So there are 4 lectures which I will be giving. So in the first one, I will be covering the front end part of an analog product, and in the second, I will be covering the second, the backend part, the physical implementation of a chip, and then we will take up one example as a test case that there is a standard product which is a 24-bit sigma delta analog to digital converter, and so those I will discuss, and then there is another lecture on some advanced devices. This is what it has been scheduled. So now, what is the basic? Now this particular thing is pertaining to only the analog part. So now we will discuss what is the how we do carry about the analog design. So there is no general methodology, there is no general design flow. Flow is there, but there is no like a specific route, or you can say an algorithm. In the sense you can put the specification and it will generate a circuit. That is not possible. When you do analyze a circuit, there are algorithms. Computer can solve it, but if you tell like a program to generate a circuit, that is not possible in an analog circuit. Synthesis is different, where you from an RTL you generate a combinational circuit. That is different, but for an analog it's not possible. So there are various approaches which are used. All sorts of approaches are used in designing these analog circuits. Now there are various level of abstraction. On the top, if we see like an op amp, we let's take an example of an op amp. So op amp at the abstract level, it's a just a symbol we use, and but once we go deep inside that block, so there may be around 10 or 15 transistors, and if we go deep within the transistors, so we will have to know about the device physics, about the so at the top there's an architecture level in terms of transistors, and then within the transistors the device physics, and particularly if you are designing at a lower node, which we call it a deep submicron node, so quantum effects also comes into picture. So this, to be able to design analog circuits or any circuits, so the solid state knowledge of the solid state physics, semiconductor physics, device physics, circuit theory, and mathematics. So all these, a combination of these things are required. And then since the number of transistors are getting increased, and the modeling part is also, there are around 97 parameters of a transistor in HSpice model, which is a BSEM 3v3 or BSEM 6 version also has been released now. So to solve those equations, it's not possible. So you have to use some EDA, some CAD tools to be able to simulate a circuit, to be able to lay out a circuit. You should be able to connect various transistors with each other, and then finally you should be able to calculate the parasitic value and take parasitic values into effect while doing the simulation, so that the end result works. So this now this involves a very good modeling, the device models of all components, passive and active. So this another which means the EDA tools, the knowledge of EDA tools, how to use these tools, and how these tools fit in a design flow. This also, there are two lectures which we are covering pertaining to the flow, or while using the digital simulations and analog simulation, how to do. Now in the last 20 years, the trend has been in the CMOS, the scaling means the dimensions, all dimensions, lateral and vertical, they are falling over the last 20 years. So what is the effect on design of analog circuits particularly? The scaling has been done for, it has benefited the digital part, but not the analog part. So let us see in this, if this table, if you are able to see, so we have chosen 0.25, 0.18 and 0.53 microns. So you can see the ion is almost same, 600, 600. At 0.13 it has decreased to some extent, but we can say it is almost same. But see the I of current, which is in picoampere per micrometer. So at 0.25 it is 10, and now at 0.13 it has increased to 320, which is, you can see, is 30 times. So what is the effect of this? What is the meaning of this? Means ion by I of ratio for a transistor. When we see what is the most important attribute or most important characteristics of a transistor, it is the ion by I-off ratio ideally has to be infinite, because I-off has to be 0 and ion has to be maximized. When you design a transistor, you design maximizing the ion. But you 600 is an 600 microampere per micrometer is an ID sat, which is an ideal value, keeping in the various implants. You cannot end the mobility at those implants. You cannot have more than this. But ideally, I of should be very, very low, almost zero, so that an ideal transistor ion by I of will be very almost infinite. But practically, it is not a good transistor which where ion by I of is 10 raised to the power 5 or 10 raised to the power 6 order is supposed to be a good one. But if you scale down the transistors, ion is we can say it's not falling that much, say 90% falling, but I of is increasing 30 times. So the overall ratio ion by I of falls. So what is the effect of that? The effect of that is like you have more power consumptions, you have more leakages even when the transistor is towards the off state. Delays we can see is a big advantage. It is falling, of course. It will fall from a 45 picosecond to 15. So 1/3 delay has decreased to 1/3. And the reason for this is basically your channel length has decreased from 250 nanometer to 130 nanometer. It's half the distance. So now the electrons have to travel half the distance, but the channel is highly now the resistivity of the channel changes because of the doping level. So there is a constraint on the mobility. So exact the delay which should proportionate falling of the delay doesn't happen because the mobility also falls to some extent, but overall the delay decreases. So this is one advantage in these transistors when the delay decreases. If we go directly to last column FT, so FT falls, we can see from a 30 gigahertz to 80 gigahertz. So FT is the cutoff frequency. What is the meaning of it? There are two important terms. One is FT, another is F max. So FT is a cutoff frequency. So this means where the current gain is both are same ion, the input current and output current is same at a particular frequency. So that is the frequency. As we know, a MOS transistor, the input is a gate oxide. So it won't take ideally the DC current will be input DC current, which is a gate current will be 0. But since there is an input capacitance, which is a CGS, so at higher frequencies, the capacitance will become very less. So it will take some current. So that will be the input current. And when the ratio of output current, which is an IDS, to input current, which is an IG, is same, or the log of this is 0, so that is the frequency, we call it an FT. So as a thumb rule, you should be able to design circuits which are around 6 divide FT divided by 60 or 80. So as a thumb rule, the operating frequency can be it gives a fair amount of idea, like by using those transistors, what kind of operating frequency of the circuits you will be able to achieve. Another thing is, you see the fourth row, which is a GM, is very, very important parameter. So GM is a slight increase is being felt from like from 0.25 it is 0.3 micro Siemens per micrometer to 0.6 microsiemens per micrometer at a 0.13. So this is one advantage. Transconductance is a mutual transconductance GM. So this increases. So this is an advantage. All the capacitances, they will decrease, and the reason is your geometries are decreasing because the capacitance are directly proportional to the area W into L, WL. So when the sizes, when the geometry decreases, the capacitance will definitely decrease. So this is the result which is being shown in these columns also. So your CG and like CGS, CGD, those and the junction capacitance, the diffusion capacitance, junction capacitances, both they will decrease. These figures are given in femtofarad per gate. VDD is falling as we have seen, and from 2.5 to 1.2. The reason for fall of VDD is like if once you reduce the length, the electric field, if you retain the same VDD, the electric field which is V by D, it increases. And once the electric field increases, there are severe short channel effects, and to contain those short channel effects, you have to decrease the VDD also, so that the electric field doesn't increase beyond a particular limit. And another reason is for an FT, because the VDD also is has decreased, so that the input level now they don't have to change to a very high level. So then, like from 0 to 1.2, earlier it has to go from 0 to 2.5. So the rise time will definitely be more. But if the input level has to increase from 0 to 1 volt, the rise time also will be comparably less. Another important parameter of a transistor is the gain, intrinsic gain, which is GM R0. GM increases by scaling, but output conductance or output resistance R0, it decreases. So the overall effect is GM R0, which is a gain, it decreases, and you can see here it has decreased from 39 to 14. So now what is the effect now if we want to design analog circuits, if we want to design amplifier, so the gain of these like low geometry transistors are very small, like 14. So if you have to design an op amp where you need a gain of say 100 dB or 120 dB, which is 10 raised to the power 5, so it becomes very difficult to use these kind of transistors. So that is the reason. Now in brief, these small transistors, they are good for the digital part, since you get advantage in terms of FT and delay. And because your FT is more, you can design digital circuits which operate at a very high clock rates, because the delay is less. And another advantage, since the area which these transistors take, it is less, you are able to put more number of transistors in a given area, so that more functionality is achieved. And your voltage level is also low, so you are able to save some power, because the power is CV square F, it's a voltage square. So you get additional advantage, since you are reducing the power, and you are reducing the voltage, so and the power is directly proportional to square of the voltage. So that advantage you are able to get. But for an analog circuits, because we are interested in a high gain circuits, and the intrinsic gain of a low geometry transistor is a limitation, it is decreasing. And another thing is, once you decrease the power, like VDD 1.2 volt, but the noise level is not decreasing, noise level is same, like for a particular transistor, if it is a millivolt RMS per hertz, so that noise will be same, but your top level has decreased from say 1.8 volt to 1.2. So your dynamic range will decrease. Now you can have output swing, which is between the noise, from the top of the noise to the top of the VDD, which is 1.2 volt. And so your output swings will definitely decrease. This means the dynamic range will also decrease. Gain will also decrease. Though you are able to make high bandwidth circuits, but because FT is high, you can have a high bandwidth, but you cannot have very high swings, and you cannot have a very good dynamic range. So with these implications, you have to design the analog part. So now we design circuit using MOS. So let's take a brief overview of the MOS transistor. So now, as I told, you have to, in simulation of a circuit, you should be able to know about the models. Now the behavior of the device is a physical behavior. It covers various effects, and like what is the effect of a mobility on doping, what is the effect of a doping, what is a velocity saturation, what is the effect of electric fields, what are various short channel effects, GIDL, DIBL, your HCI, and what is a substrate current, what is the effect of substrate current on circuits, what type of noise, what is a white noise, what is a 1 by f noise, what is a thermal noise, how does it affect the behavior of the circuits. what is the effect of the temperature on the MOS transistor, like various parameters, ID versus VGS, ID versus VDS, your input characteristics, output characteristics, transfer characteristics of the MOS, how does they change with temperature? So all these things have to be cleared uh, before we start actual design of analog circuits. And all these behavior is covered, which we call it a model, because the physical is okay, but to be able to design circuit, you need very compact models, very compact equations, so that you are able to solve in a less time. You should be able to analyze the circuit in a less time. That is the requirement. So for those, we need very compact models or compact equations, and it has to cover the various geometry ranges. Spice model. So these are the various models which are being used by the industry. Spice, BSM, right? We are using BSM 3v3 now. BSM 5 has also been released. Philips models, EKV, then SP and PSP models. So these are some of the models, but most common of these are BSM and BSM 3v3 and BSM 5 models. And some people are also using EKV models. They are very compact. They take less time in simulation. A compact model is having the behavior of the device is explained in terms of like very compact equations. And as we know, the MOS transistors has various operating ranges, like from the cutoff, then saturation, then the triode, and all these ranges inversion, like and there are again 3-4 ranges within the inversion: moderate inversion, weak inversion, strong inversions. So there is not a single equation which can describe the behavior of the MOS in all these different regions. So the objective of the modeling is to have a very compact equation which at least is able to describe the MOS transistor across the various regions and across the various geometry also, depending on the different W and different L. So this is the basic cross section of a simple device, and you can see this is the equation where we are covering weak inversion and strong inversion, and between weak and strong there is a moderate inversion which is not so well defined. But you can see in a weak inversion where VGS is very less than VT, and this equation is all, it's an exponential equation. The current, which is an IDS, it depends on e to the power VGS divided by eta and VT. So it's just like a base current of a bipolar device. It's an exponential behavior. But in a strong inversion, it is VGS minus VT square, which is a like a square relationship here. And in a linear region, triode region, where VDS is less than VGS minus VT. So these are the VT is thermal voltage, which is 25 millivolt at 25 degrees centigrade. So these are the basic equations which we can use in a strong inversion. We have to say of mu naught Cox is a technology parameter, and W by L VGS minus VT square. Now for a circuit designer, in this equation, he cannot change mu, he cannot change Cox. Only we can change the physical geometry, which is the W and L, and the voltages VGS. VT is also fixed. It's a technology parameter. Threshold voltage cannot be changed, but you are free to change the voltages, all voltages, gate voltage, drain voltage, your substrate, your source voltage, and you can change the size of the transistor. When VT is fixed, mobility, Cox, all the layers, they are fixed. They are not cannot be changed. So now let us see in a brief about these regions. So first is a weak inversion cutoff region. We will not use the cutoff region is used only in digital design, where it's the transistor is acting as a switch. So we operate the transistors in a cutoff and the saturation region. But for an analog, we operate in the moderate region the moderate inversion and weak inversion regions also, there are certain advantages in doing so. But so we will see what are those advantages. So weak inversion, it's just like a BJT in the sense that the current is exponential. It is e to the power VGS divided by eta VT, which is a thermal voltage, and eta is more than 1, so it's 1 point. It depends on the doping, or how, or what kind of transistors you have made. So eta depend, normally it is close to 1.4 or 1.5. Now this region, the transistor will be slow in this region. It you cannot have very like high, very high FTs, but the advantage is why this region is used. You get very low power. The power dissipation is very low, and we can get even a moderate speed even in the weak inversions, by where the L is for a short length, short channel devices, we can get reasonable speed in the weak inversion also. But the disadvantage is matching. Disadvantage is matching the, because in an IC you see many transistors have to be connected, they have to be placed together. Those transistors have the parameters, particularly they have to be matched in fabrication. If the transistor doesn't match, then mismatch effect will result in some of the specification getting out of the whatever the desired targeted specifications are. Like you have seen the differential pairs, the differential pair has to be matched. There should not be any offset. If it is not matched, the offset will be created. Mirrors, if you have a current generator, so you will have a current mirror, you will make various current sources based on that. If the transistors are not properly matched, if slight difference in VT, it the current will not be exactly replica of that, but it will be. Are you able to hear me? Oh.
They got reconnected.
Okay.
Automatic sound.
That's okay, but you are able to hear me, or just if there is any question in between, you can stop me.
Any of the center can reply. Anand College, Rajasthan. क्या आपको आवाज आ रही है?
कौन सा जबी ये?
So if you have any queries, you can stop in between also, or you can write on a piece of paper at the end of the lecture. You can ask, or you can stop me during the flow also. So this matching, when you fabricate, manufacture many transistors on the same die, so matching is very important. If the transistors are not matched properly, then the overall circuit performance cannot be met, particularly in a differential pair, or where like for a 1 nanoampere current source, you have to make many 1 nanoampere. If the transistors are not properly matched, it will not be 1 nano, it can be 0.9 or 1.1 nano. These things we will see, and how to improve the matching, that also we will consider. Mainly the VT in a wafer, you see like in our technology also, it will differ by say 40 or 50 millivolt. So what will be the effect of two transistors which are placed very close to each other? If their VT differs by 40 millivolt, what is the effect? So this you will have to see in the while putting that particular parameter in the SPICE models, and then you have to see what kind of effect it is having, a mismatch of a VT of say 30 or 40 millivolt. Now most of the time most of these designs, the transistor is used in a strong inversion region, and the reason is we get the maximum gain under this. This is the most common region, and depending on the values of VGS and VDS, you can force the transistor in this particular region. And equation is it's a square behavior, like the current is proportional to VGS minus VT square. So this is the triode region. The advantage of, you can see, of a triode region, VGS is greater than VT, but VDS is less than VGS minus VT. So the field, the channel is uniform as you have seen, and current is proportional to VDS, directly proportional to VDS, as you can see here. And for a small values of VDS, for a small, if the VDS is small, we can ignore this VDS. Then ID versus VDS is becomes a linear function, means the transistor acts as a resistor also. So this region is used in for using MOS devices as a transistor, and so you can control the MOS and use MOS device as a resistor, and the value of resistor will depend on the value of W and L, but you have to be careful. The voltage across that resistor has to be accordingly, so that the MOS is in always in triode region. So this is the saturation region. Pinch off starts, as we have seen. This effect is shown, and this equation is square. It's a square law device, we call it, and this is the most common region. And the advantage is you get the maximum gain in this region. And now, so what do we mean by design when we say we have to design an amplifier? Designing of the amplifier means one is the circuit topology. Circuit topology is given in most of the books, but the design means what will be the sizes of those transistors, what will be, you have to find the sizes of the transistor and the operating point, the DC operating point. And the DC operating point will be in terms of VDS, VGS, IDS, and the sizes will be in terms of W and L. So these are the things you have to find. This is what the design mean. So whenever a design is started, certain input things are given, like you have to design an amplifier for which it should be able to have a gain of say 100, and it should the bandwidth should be some 1 megahertz or 10 megahertz. It should be able to drive a particular load, which can be a resistor or a capacitor. So these are the given things. So the key design parameters are, like for example, in a large signal, in a large signal we have the drain current or the VDS and VGS. They both these they will decide the drain current, and drain current will decide the power dissipation as well as the slew rate. If you want the slew rate to be very steep, very high, you should have a very high drain current. But if you are having a high drain current, then your power dissipation will increase. So these are some of the effects, and wherever you do the the way you bias the drain, the VDS voltage, it will also decide your swings, the output swings, the over voltage, particularly the VGS minus VT, which is an over voltage VOD. How much, as we know, the transistor is on if the VGS has to be greater than VT. But how much greater? VGS minus VT, which is known as a VOD, overdrive voltage. So the overdrive voltage, it decides your output swings. If your overdrive voltage is very high, your output swings will be less. So we will see in some of these practical numeric values how these things are. Now the small signal parameters which are of importance is a mutual transconductance. It will decide the speed. Then the various capacitances like CGS, CGD. Again, CGS, CGD, they are dependent on the geometry of the device, W and L. They will also decide the speed or the bandwidth. Then the output resistance R0, which will define the gain. If your output resistance R0 is high, your gain definitely will be high. If your output resistance is R0 is less, your gain will be also not very high. So these are some of the key design parameters. Now threshold voltage is very important. It is given by the technology, and you have to like these are the approximate values. Say if we take a transistor which is having a channel length of 0.5, so the VTs will be normally close to some 600 millivolt or 700 millivolt, and the power supply is close to 1.8 volt. And this VT cannot be changed, but this VT of a transistor is fixed. But what you can do is you can have a body bias so that the effective VT you can change. So this way, by increasing the VBS, as the last line says, bulk potential increases, the value of the VT also increases for an NMOS. So that way, dynamic VT shift you sometimes you can do if it's required in your circuit. So VT is not constant for all transistors depending on the transistor length. This is the what plot it says. VT is fixed for large channel transistors. As you can see, if the channel length is large, 10 micron till 1 micron, you can see this flow, this graph of VT is almost fixed, say around 660 millivolt. But once the channel length falls below 1 micron short channel effects start appearing, and you can see it how the VT can drop, because if the channel length is low, the VT starts falling, and it can fall by some 50 millivolt or 40 to 50 millivolt, as you are seeing here in this. Why the VT should fall? Because low channel length. This is the because there is a voltage at the VDS, so that also, because finally you have to, what is the VT? VT is a voltage where you have to invert, you are able to invert the charge in the channel, and once the channel length is decreased, it is getting smaller, the drain voltage also contributes in inversion of charge, so less voltage is required at the gate to invert the channel. So that is the reason why VT falls at short channel length devices. So another mu naught Cox is a technology parameter. This is the current equation only. I have written in a different manner, but you can see this mu naught Cox. It is directly proportional to Gm square and inversely proportional to ID. So for a small values of current, like near weak inversion region, the value of is very small, because if the current values of ID is small, the value of mu naught Cox will be small, and it rises sharply as the transistor moves towards strong inversion region, and it again falls at large values of current because of the velocity saturation effects. So you can see this is the behavior of mu naught Cox as plotted with respect to VGS. So our threshold voltage is close to 600 millivolt. We have assumed 0.5 or 0.6. You can see at 0.6. So this is the behavior. Red one is for an NMOS. As you increase the VGS beyond threshold voltage, the technology parameter, which is also mu naught Cox, so it increases and reaches a top, and after that it starts falling. So why it starts falling? Because of velocity saturation. The velocity is getting saturated, and even if you increase the VGS, there is no effect, and finally it starts falling. And for N and P MOS, both these curves are shown. Before before start of design of any analog circuit, it is essential to understand how these parameters behave with different voltage, because these parameters are not fixed. As you have seen, VT is also not fixed, mu naught Cox is also not fixed, it varies. So this the behavior should be known. Now let us see GM, transconductance, mutual transconductance. So it affects the gain and speed, gain GM R naught, and it in the speed also, in the bandwidth also GM will come. So this is the GM in the weak inversion region, which is an your current will be an exponential function, and it will be ID by eta VT. And in a strong SI, strong inversion region, these are the three basic formulas, or which you can easily get by by differentiating ID with ID del ID by del VGS. You will get all these formulas. So you can see V over drive. So GM is equal to 2 ID by V over drive. If you have biased a transistor at a fixed current ID, then your drive VOV will define the GM. So if you want a high GM, you should have V overdrive plus a small value of overdrive. Then you will get a high GM for a fixed ID if your ID is fixed. So near weak GM will be, so for small values of VGS near weak inversion, we have seen the GM will be small. In the weak inversion region, the absolute value of GM and ID will be small, so only low speeds can be obtained. So the right now there is a trend to design circuits in the weak inversion region, and the reason is only slow speeds like a bandwidth can be few hertz only, say some less than 100 hertz bandwidth, but power dissipation can be very small in nanowatts. So these there are many applications where you need circuits which have to operate at low speed, which are low bandwidth devices, but power dissipation is it has to be very small. And many of these examples are the electronics which is used in medical applications, particularly the devices which are implanted inside the body, like there is a device which is implanted inside the heart, and to generate that electrical signal of the heart pacemaker. So the device, it doesn't require a very high bandwidth, but it's a very like some less than 100 hertz, but the power dissipation is very crucial, since it has to be operated by using a battery. So, and the battery must last for 10-15 years, so you have to design a circuit so that the power distribution is very small. So in that, if you design a circuit where the transistors are in strong inversion region, it will consume huge amount of power, so you have to design in a weak inversion. So there are many applications today where the circuits are designed in a weak inversion region also. So in the velocity saturation region, where the velocity is saturated, this means the drain current, first of all, why the velocity will be saturated? If you see, if you increase the field, the electron is getting accelerated because of that field, it will increase, the mobility will increase, but at some point the mobility gets saturated, that is the voltage at where the electron mobility gets saturated. So that is a velocity saturation region. In that region, the GM is not dependent on VGS. If you keep on increasing VGS, nothing will happen in this region. And so this is, if you see the plot of GM with respect to VGS, so here also VT is assumed to be 600 millivolt. So you can see the GM. If this is the point, let us take for an NMOS, which is a red curve, and in the weak inversion, the GM will be less, where weak inversion is where the VGS is less than VT, less than 0.6 volt. You can see here, but in a strong inversion region starts here, the GM starts increasing. Now it depends on the overdrive. If you have more overdrive, you can see here how the GM is performing here, and finally it flattens out. So same is the case with a PMOS. So this is a GM plot of a diode connected MOS. So these are the various capacitances which play important role in deciding the bandwidth CGS. There is a junction capacitances here, and here there is a sidewall capacitance here and here also, and this is the gate capacitance. So gate capacitance also is two types. One is due to gate, another due to, there will be depletion region, there will be another capacitance due to depletion, and there is an overlap OL capacitance between the drain gate and source gate. So here the capacitance, actually, if you see overall capacitance, there will be one unit capacitance, and then the overall capacitance will be depending on the area, which is W into L. You can see this is L, and inside this figure is the W. So that will be the geometry. So WL and some basic capacitance like WL into Cox. So this will be the total capacitance. So that is why if the transistor is smaller, the total capacitance will decrease. So this is a small signal model of a device. So this is the gate, this is source. So we will have some like GM VGS, a current source here, this one, and in the input side there will be a CGS, gate to capacitance here, and then gate to drain capacitance, then gate to body, and then this is body was also shown where the current will be flowing from the source to the gate, and we have an output conductance or an which is known as a G naught or a GDS or an R naught or an RDS. Different books have different notation. This, and then we have a source to body and a drain to body. So this is overall, but starting, I have a point here. If you start with this model, and if you draw a very simple circuit and replace the transistor with this particular model, it will be some effort for you to solve those integral differential equations. So for a learning point of view, the best is you have to start with a very simplified model. In the simplified model, I mean, you can eliminate all these capacitances first and then solve the circuit. Then you have to consider only the gate, source, GMVGS. That's all. This GMVGS and this. Or if you, is it possible to write on the board?
Yes.
No. So I can just show you because this is very essential if you have to learn analog design.
इसमें की ये ना जो ड्रॉ इसमें डस्टर और वो पड़े हैं नहीं ये कीबोर्ड वाला ओपन करो हाँ इसमें मार्कर और डस्टर होगा हाँ ही चलता है
ये परमानेंट बात करते हैं ना?
नहीं नहीं इसे परमानेंट नहीं
तो व्हाइट बोर्ड हाँ ठीक है
आप कैमरा घुमा दीजिए
So now let us see any. This is source, this is gate, this is drain. So body is connected to source. So this is the model which has been shown on the PPT. This is a complete model, but if you replace, like for example, let us take a very simple circuit. I will draw only the small signal part. Suppose you have connected a source Vs here, and this also is connected to ground, and you have connected a load RL. This is VDD, and you want to calculate what is V naught. Okay, so this now you have to replace this with this small signal, and you have to analyze. You have to calculate V naught by Vs. V naught by Vs. But if you do include all these elements, you will not be able to get a feel of the circuit. So the first is you start with a very simple, like you have this model first. This is ground, this is source, this is your gate, this is drain, this is VGS plus minus VGS, this is GM VGS. This much only. So you can see you replace this with this, you will immediately get the value of the gain. So it is very simple. It's very straightforward here. So what we have assumed, these are ideal transistors. Like in the sense, this is ID, this is VDS. So the transistors are like this. They are flat curve. So that there is R0 is infinite. So I am not putting any R0 here. But because of short channel effects, this is not flat, and this is VD sat. The current do increase here, the current remains constant if even the VDS is increasing. VDS is increasing, the current is constant. So then R naught, which is a slope of this curve, inverse of slope of this curve, will be infinite. But this is for ideal transistor, but or long channel transistor, this is true. But for real transistor, there will be some increase in current. So these curves will be slightly tilted like this. It will be like this. So this means some R naught is coming into picture because now you have a slope. So inverse of slope will not be 1 over del ID by del VDS will not be infinite. It will be some specific value. So first is this, and then you go to the next version of this. You put that value, which is an this thing. You do like this, which is sometimes known as R naught or G naught or RDS or GDS. All these terms are same. You solve again this. If you do this, here gain will come minus GM naught, minus GM naught. If you do this, the gain will come minus GM R naught parallel RL. Here it will be minus GM RL because R naught is infinity. So here it will be RL parallel with R naught minus GM. It will be the gain. So this is the second, and the third. Now this is a, we are not assuming any capacitances. Now you start adding these capacitances. There are three. There are capacitances at the gate, at the drain, at the source, and between gate to drain. Between gate to drain. Overlap capacitance gate to drain, gate to source, drain to ground, source to ground, but source is already ground, so this capacitance will not matter. So those capacitances also you add one by one. Like first you add the capacitance here. So what you will do, you will put a CGS here. Then you do this GM, VGS, and this is R naught. This is ground. We have not assumed the substrate effect because this body is connected to ground here. So if there is a R here, then R will come and the body potential will be same. That effect has, then VBS will come. So I am now directly shorting it here. This will be drained. So now you can see here. You see in this model, what is the difference here? It will, if there is no capacitance in this circuit, the bandwidth will be infinite. So this transistor, you give any input signal Vs of any frequency here, you will get the output. So you can give any input signal of any frequency. So what is the hindrance? Because there is no VGS here. So once we put a CGS capacitance here, right, and then this capacitance now, if there is a fast, this node, potential at this node has to be changed because this is Vs here, like saying that. So if the potential at this node has to be changed very fast, then only the output will change here at the output. This output will track this. Since there is a capacitance at this node, the potential at this node cannot be changed that fast. So there will be slow. If you give a very high speed signal, it will not get time to change to respond to that potential. So you won't get any output. So that is how the limitation comes in the bandwidth because of these input capacitance. So input capacitance will restrict your bandwidth because your source is getting connected like this, RS and VS here. If this capacitance is not there, whatever VS fast signal, it directly comes here. But now there is a capacitance, and as we know, the voltage across a capacitance with respect to time, it changes like this exponentially. Okay, so V is equal to V naught e to the power minus T by RC, depending on the value of RC. So it will change, but if the capacitance is not there, the voltage will change like this. So there is no delay. So finally, in the physics point of view, means there is basically the electrons have to move from one place to another place, and the movement of electrons from one place to another place, it will take some time. It cannot be in zero time. So that is the reason, and why we call it the gain and bandwidth is fixed, right? Gain bandwidth GBW. So if you want high gain, you cannot have a high bandwidth. The reason is that only because the charge has to move from one place to another. If you want high gain means more charge, and high speed means very quickly. So it's not possible. If you want less charge, you can move it at a very high speed. But if you want more charge, then it will be, you cannot move it at a very high speed. So that is the reason the gain bandwidth is fixed. And so you do, so there will be a pole because of this that will restrict the bandwidth. So in the response, if you see, if we are getting, this is your Bode plot where this is 20 log of gain, and this is your frequency. It is showing GMR naught. This is GMR naught. Gain at all level for an ideal transistor. But if you have a CGS, definitely at some point you will get first pole, and at first pole this start falling by 20, like this. By 20 dB, the gain starts falling at 20 dB. So your bandwidth is only this frequency, and this frequency can be calculated. And next, there will be a capacitance at drain to body also. So in the next, you put this capacitance, which is VGS, and then this is GMVGS, and then this is R0, and then you have put this CDB. So there another pole will come because of this CDB, and since this dB is less than CGS, so this pole will be further away, maybe at here. So at here another 40 dB fall you will see in this. Okay, so this way you keep on adding. Now there is a third. Next you go to the next. You have to put another capacitance, which is CGD. Now this is a Miller capacitance because this is connecting input and output both. So this capacitance can be split in two parts, CGD. So CGD you multiply by the GMR0, and you can bring this capacitance to this side, and you can bring that capacitance that side. And then these two circuits becomes independent. You can write the nodal equation and solve these circuits. So this way, if you try to analyze, you can it becomes easy for you to analyze the circuit, and rather than going straight for the complete model. So these are some of the values of the capacitance. I will skip these things, and output resistance we have talked, and which is 1 by GDS. In some book they call it resistance, in some book they call it output conductance. Both are same, and for long channel devices this is almost infinite, but this is not the case for a short channel devices. So this you can see here how it varies with respect to VDS, both for an NMOS and for a PMOS. Another thing which you are observing, this is the green is the PMOS. So R0 for a PMOS is high. So the gain GMR0 for a PMOS will become high. So wherever you want high gain, you can use a P device. This is at a length of 0.5 micron. So intrinsic gain, if you see, this is the intrinsic gain, GMR0. So it becomes high at some particular point. And as I told you, for a PMOS, the internal gain is high as compared to an NMOS. As you can see here in this graph also. And now, you see, now there is another figure of merit, which we call it a GM by ID. It's a very important design parameter, and it unit is 1 by V. So this means now the question is, if you want to have a high gain, so you should have a high GM. GM or not, you should have a high GM. So how you can have an high GM, high mutual conductance? There are two ways. Either you can have a very high, if L is fixed, you can have, because GM is equal to mu naught Cox VGS minus W by L VGS minus VT. So if L is fixed, to increase the GM, you can have a high large W. But if you have a large W, there's no problem, you will get a good gain, but your bandwidth will fall because the capacitance is directly proportional to W into L. Another thing is you can have, because GM is directly proportional to mu naught Cox W by L VGS minus VT. So for a high GM, the VGS minus VT term is coming. VGS, VT is fixed, so you should be able to have a high VGS, then only GM will be high. That is okay, but if you have a high VGS, means current is also high, ID is also high, so your power consumption is also high. So, but our goal is we want to have a gain where the power consumption is also minimized. So that is why you divide both these, GM by ID. You maximize GM by ID. So you will get the more efficient design. So this we try. So what is the technique? How do we design where we can maximize GM by ID? So this particular thing we will see. So this is what we have plotted. So GM by ID we can have maximum 20 and at a very low VGS, but at a very low VGS our bandwidth will be severely limited. It will be very, very less. But if we want to have a reasonable bandwidth, so we have to design at VGS close to 0.6, 0.7. You can see this region where normally we design with GM by ID close to 10 to 15. You can see here 10 to 15. And here our overdrive is close to 200, 220 to or 200 millivolts. And where we get reasonable bandwidth. Here you can have, okay, GMID is very good, but your bandwidth is not very high because you are in a weak inversion region in this VGS. Okay, so this is the unity current, this is the bandwidth FT. You can see this also gives, this is an overdrive. If you increase the overdrive, FT will be more. Or if you decrease the L, it's square. If you decrease the L, your FT increases. So these things are GM by CGS, all this is inversely proportional. So these are the set of equations. You can see here FT. So now how will, basically this is the summary for long channel devices, for short channel devices. Long channel devices, overdrive voltage will be 2 ID by GM, VGS minus VT will be this, it defines channel pinch off. And for short channel devices, V overdrive is not exactly VD sat, it is more than VD sat. Now, what is the basic design approach now? So how do we start with the design of the circuit? So as I told you, any design, they will give you the objective, like you have to design an amplifier which has a bandwidth of this. It is supposed to drive a particular load. You cannot design any circuit which can drive any load. You have to specify the load. And you cannot design any circuit which has infinite bandwidth. You have to specify the bandwidth, right? For very, very simple analogies, like for a vehicle, you cannot design any vehicle which can carry infinite load. It has to be some 1 ton, 2 ton or 5 ton. Similarly, you cannot design any vehicle which can have infinite bandwidth for circuit. For a vehicle, it is speed. It has to be 200, 300 or 400 kilometer. Speed have to be defined. Load has to be defined. So similarly, in the circuits, these two, bandwidth and load, will be given to you. Straight way you put this in this formula, you will get a GM. 2 pi f UGB. UGB is the bandwidth multiplied by 2 pi will, a factor of 2 pi will come, and you will get a GM. So if you have to design an amplifier, so this is the GM you should have. So now you have got a GM. Starting point is there. Now you have to start GM formula. You see mu naught Cox is fixed. W by L, VGS minus VT. VT is fixed. Now what are the variables? W, L, VGS. These three variables you have to decide. Now it depends on you. You can either pick a small L or a large L. For a short channel devices, you will get high FT. For a long channel, you will get large gain. So you can, and length also affects the noise corner frequency also. Okay, so normally what we do is, based on GM, we will put the VGS minus VT. VGS minus VT is the overdrive. So we will decide overdrive. And VOD is also, there is a limit only, like you can have between 200 millivolt to 300 millivolt. You can choose any of these values. You cannot go beyond this 200 to 300 millivolt. Now GM is also known. V over, you first choose to 200 or 220 millivolt, you will get ID. Okay, and if you want a large V overdrive, you will get a high FT, but you will not get the signal swing at the output. You will get small signal swing. If you want a large signal swing at the output, you choose small overdrive. You will get a large signal swing, but you will not get a large FT. So depending on these, normally in a design there are iterations, many iterations. So you start, as I told you, GM is fixed. You start with an overdrive, say 210 millivolt overdrive, and calculate all other parameters. You can calculate ID from here and proceed further. Once you have got an ID, you know a GM, you know the overdrive, you check for slew rate, you check for power consumption, and you, based on, you have now ID, you have fixed some L, you fix a L, and you find the W from the spice plot, and do find calculate slew power. If they are not meeting your spec, again you go to the first level, you change your overdrive, tune it, and again repeat this exercise again and again. So in few iterations you will be able to do this. So these are known as spice plots. So they are the plots plotted between, you can see here, overdrive and ID for different values of W. So this is a spice plot for a W of 50 micron, and with you can see here with different lengths, the 1 micron, 0.5 for N and P. So for different L you plot this. So what you have to do is, you have plotted these curves for different L. If you have chosen an L of say 1 micron for a PMOS, which is a blue curve, this curve for a 1 micron, and you have chosen a V overdrive of 0.25, so VOV of 0.25 and ID, so this W will be 50 micron kind of will come. So this way you are able to do this. So this is the complete flow. First of all, system, because this chip will be used in any system. So from the system specification, you have to drive the circuit specification. The circuit specification, the large parameters like your biases will be derived, and your small signal parameters like gain also will be derived from these specifications. And then you have to choose a topology. You have to partition the circuit, wave, then your basic analog, and some, you have to do some analysis. We will take this example like see, these are the various common analog structures which are used: common source, common drain, common gate, diode connected transistor, cascade, folded cascade. All these different structures are used, differential pairs in making the current mirror and cascade mirrors. So by circuit partitioning, I mean this is a example of a differential amplifier. If you analyze this, you will not understand what is the function of each transistor. So you do the circuit partitioning. So here the critical portion is the G. This is the GM structure, red. M1 and M2, they are the differential pair, and these have to be properly matched. And what is this? This is the bias structure which is giving this bias current MB1, and this MB1 has to provide a bias current for M1 and M2, and this bias current is taken from I bias and with this particular transistor. So you have to adjust the WL of this and this, so that whatever bias current you want, you can generate from this I bias. This is the load. This is the load structure. Okay, so now your the GM of this M1 and M2 is important in deciding the gain of this transistor, whereas these are for biases only. And these here, the output swing also will determine the VOD at this particular. So the gate voltages at this point, VGS, will decide those. So this is the circuit partitioning thing. So GM structure, it converts input to an output current. So common source, these various two stages you can use in this, and you can have, this is a single stage amplifier, you can have a two-stage amplifier. So first stage and second stage will be your common source and a current bias current mirror. So you can have bias structure. GM structure requires a current bias I think any cascode structure requires a voltage bias and all these things. I think I will skip. So basically, is from this is how you derive the specifications from the system level to the various circuit level, and from the circuit level to the load to the GM to the bias, and you make a series of amplifiers. So depending on the system requirement, all these specifications will flow with each other. So this is how you derive these specifications, and this is a very basic formulas like GM R naught. Gain bandwidth will be GM by 2 pi CL, and phase margin will be, you can see, you can calculate. You need not use the simulation. You can calculate these with these simple formulas, which are, and overdrive output swing will be supply minus overdrive, and your whatever currents are flowing, this summation of all branches current is the total current, and power slew rate will be I out by CL. Like if you want a high slew rate, CL is the load capacitance is given, then I out. What is the last stage? Last stage means this stage. This stage. So this is the last stage. This will be driving a CL. So the I out of that has a direct bearing on the slew rate. Okay, so and you similar in the same way you can calculate the noise. You have to refer the noise to the input side, and you can calculate the offset. You can calculate all those rejection ratios by these simple formulas. And this is the one example. You can see this is M1, M2 here. PMOSs are used because I want more GM. So this is the biasing network. Bias is obtained from I bias, and this is the active loads, this MB1, and no, so this is the bias, and this is the active load, and here another stage is there, and this is the CL. Now the slew rate will depend on this current I2, because this I2 has to feed to CL. If you want a high slew rate, this you have to make I2 very high. So you can see here the what is the current consumption, I1, I2 plus these are the branch currents, I1, I2, and another current I bias. So this is the total current which is flowing from VDD. So you add these current, multiply by VDD, this will be your power consumption. So what is the gain output resistance? You can see here output resistance by looking at the circuit. You can calculate. You can see R out will be GDS12 and GDS34 at the one stage. So it's a very simple at the one stage. So here the output of this is taken here. So here what is the output you are getting? A GDS one means M1 and M2, they are exactly matched transistors. So what will the output here? You will get a GDS of M2 or M1 and GDS of M4 or M3. So these are matched because the same these M1, M2, M3, M4 are matched at this point. And similarly, what will be the output here? Output resistance. These two transistors will come into play for the output. So this is a GDS 5 and of this. So now you can have a common mode input range, means what is the minimum and maximum voltages at this level which you can give, assuming this VDD. You see, you have to keep in mind that these transistors, all these transistors, this and this should be in saturation region. Okay, so now you see here, you start from here. For this transistor M3 in saturation, what you have to do? So this is VGS here, and gate voltage is connected to the drain. So VGS should be more than VT. So this, what should be the potential at this node? It's not coming. Yeah, here, what should be the potential at this node? So this point should be at least, this is VDS. Okay, one VDS above. And now what should be the voltage here? Another VT, because this is VGS, right? This is gate, this is source. So gate should be 1 VT above, and this is VDS. So this is the minimum voltage you can give here from ground. You cannot give zero voltage here. If you give zero voltage, what will happen? These M1 and M3 will not be in saturation, right? So you have to give a voltage which is higher than zero. Similarly, if this is VDD, and what is the higher voltage here which you can give? You have to make this particular these two transistor in saturation. So that way you have to decide all these by looking at these pictures. So this is what are seeing. So this is a minimum voltage, and this is a maximum voltage which you can give, which can decide your common mode thing. It is like not very difficult to understand, and you can see here, like let us say this formula minimum voltage is VSS. This is VSS, which is ground. Then you will have VGS of 3. VGS of 3 is there. You can see VGS of 3 and 4 are same. VGS of 3, and then overdrive of VT, and VGS 1 of 2. Right. So this voltage VSS, if this VSS is 0, then it will be 0 only. So this transistor you have to make in saturation. What is that? VGS is required. Then this transistor you have to make in saturation. VGS of this voltage plus overdrive. So these three you will add. So this is how you will calculate slew rate, input referred noise, and CMRR, PSRR. CMRR you can see depend on GM by DSB, and PSRR by this. So all these parameters you can calculate, and then redo your dominant pole. That all it is also very easy to see what will the dominant pole, and because the dominant pole will be decided by the CC, will be decided by this node. So here this node, this is the CC, and whatever conductances are coming at this node, which will be the GDS of this transistor, and GDS of this transistor will add up in multiplying with this node. So this will affect your first pole. So this is your first pole R out, and a gain of the second. So this way you can decide all these parameters, gain, bandwidth, and rest of the things. So here again the same. If you partition the circuit, it becomes clear. This is the differential pair, this is the load, this is your biasing, and this is a common source. And you can, here P are chosen, you can have a choice of NMOSs here. If you have NMOS here, you will put a PMOS active load, and bias you will put down here, and here also you can have, then a PMOS will come here. So depending on your requirement, you can have these. So these are the derivation of specification. Like differential pair will decide the GM12, GDS2, CMIR, noise offset, gain, bandwidth. They are dependent on M12, right? And this load, the stability of gain, noise offset, this will depend on load, and a common source will decide your gain, output voltage, and stability. So these three, each stage will define something, and current biases will also define CMIR and the voltage range. So each stage will define some basic things, and based on this, so this is the design sequence. So you will be given a slew rate, and based on the power consumption. So because here what is given to you, you are given, you have to design a circuit which has a bandwidth, which has to drive a load, which has a particular slew rate. So based on these slew rate, you define some, you start with some initial values, you put those values in the differential pair, and then in the load circuit specifications will also come based on this. And since you have to decide the value of over VOD, so VOD will depend on the output swing, whether you want low or a high, and gain already has been defined because GM already will come into the picture, and you adjust these values, and then finally you calculate CMRR, PSRR, noise, and if it is not making, then go again here, change the VOD, change a little bit TL, and again do this calculation. So you keep on repeating all these steps till all your parameters are chosen. So as a thumb rule, some of these things are given, like CC you have to choose. So what if your load is given, you have to choose 0.2 times the CL, or 1 by 5 1 by 5 times of CL, you have to choose this compensating capacitor to get a, normally the phase margin should be between 40 to 60, or no, preferably 50 to 60. If you are able to achieve that, is better. And so normally IT is around 10 times than the I1. The first whatever the current in the first stage, the second stage normally is around 10 times to meet the gain and stability. These are just as a thumb rule, not fixed values. So this way you can calculate, and this also again it's those steps only are written which I have explained to you. So you can see this, the gain of GM1 5, if you GM5 transistor and one transistor, this is how the curve, the if you want to have 60-degree of phase margin, so you have to follow this red, most of these red path. So you should have GM fifth transistor and one transistor should have a ratio of 10 almost, then only you will get close to 60. If it is 5, then you will get like below 60, but above 60 you have to have this 10 kind of thing. And if you go beyond 60 here, it's okay, the phase margin is getting improved, but your GM is like GM5 has to be very high. GM high means again your then ID will shoot up. And so though there is a compromise, you cannot get all these parameters good, so you have to finally a compromise is there. So that is how you have to choose these biases. And this things, these are some of the excellent books, which is one is a Behjad Razavi, another is Allen Phillips, Allen Hallberg and Douglas. So there is one paper also. This is a very good paper. So you can refer to, it's an IEEE journal, and where this methodology of designing is given.